In this presentation, we have talked about Gauss divergence theorem. Gauss divergence theorem relates surface integral and volume integral. First, we should know the meaning of the term surface integral. For that, come to this diagram. Here, S is a closed surface, and we have chosen a smaller surface, that is infinitesimal surface inside S, called ds. Suppose the surface S is having a fluid. Fluid means it may be a liquid or a gas. The amount of fluid coming out of the closed surface is estimated with the help of our surface integral. For that, consider a vector f normal to the smaller area ds, and the product of f and area of ds will give the information about flux. Flux means the amount of liquid coming out of the smaller region ds. If you want to measure the amount of liquid coming out from the entire surface S, just we have to take the integral. Now read out this statement. In fluid dynamics, the net rate at which the mass of the fluid leaves a volume bounded by a surface is called flux. The flux d pi of a vector f through an infinitesimal surface ds is given by d pi equal to f dot ds. The flux d pi is the component of vector f normal to the surface ds multiplied by the area of the surface ds. That means vector f into area of the surface ds, which will provide the amount of fluid coming out of the smaller region ds. If you want to measure the amount of fluid coming out of the entire system, just you have to integrate this. The total flux is obtained for a finite surface by integrating f dot ds over the entire surface. So this is the usage of surface integral. If you think about volume integral, the flux is also studied in terms of volume integral. If you want to measure the flux in terms of volume integral, we have to assume that the volume bounded by the surface S is known. You may come to the conclusion about the amount of fluid coming out of the entire system S. In the case of surface integral, we are expressing the amount of fluid coming out of the system in terms of area. But in the case of volume integral, we are describing the amount of fluid coming out of the system in terms of volume. That means volume bounded by the surface S. Now consider this diagram. X, Y, Z. Assume that f is the vector. The component of f along the x direction is fx, along the y direction is fy, and along the z direction is fz. Here dx, dy and dz are the sides. Dx is along the x direction, dz is along the z direction, dy along the y direction. This is left face, this is right face. Then bottom and top faces are along the y direction. Front and back faces are along the z directions. Now, read out this. Consider an infinitesimal volume delta x, delta y, delta z. Infinitesimal means very small. We are taking very smaller volume, delta x, delta y and delta z, and a vector f with the components fx, fy and fz along the x, y and z directions respectively. Now we are going to calculate the outward drawn normal along the left side and the right side. If f be the vector, the component of the vector along the x direction is fx. Here the outward drawn normal along the left hand side is minus fx. To calculate the normal component of f along the right side or right face, we should use our Taylor series. See this, the outward normal of f on the left face in the x direction is minus fx. If the vector field changes between the left and the right faces, the normal component of f at the right face can be obtained using Taylor's theorem. See, this is fx plus dou fx by dou x into delta x by 1 factorial plus dou square fx by dou x square delta x square by 2 factorial. Next term is plus dou cube fx divided by dou x cube into del x cube by 3 factorial. This series is going on. If delta x is very small, we should neglect the higher order terms. Therefore, the normal component of f along the right face is fx plus dou fx by dou x into delta x. This is the normal component of f along the right face. The normal component of f along the left face is minus fx, along the right face is fx plus dou fx by dou x into delta x. In the same way, the normal component of f at the bottom face is minus fy and the top face is fy plus dou fy by dou y into delta y. See, bottom face, top face, which are covered by y axis. In the same way, the normal component of f at the back face is minus fz and at the front face is fz plus dou fz by dou z into delta z, because z axis is covering the front and back faces. Now we should consider the left and right faces. Now the outward flux of f over the left side face is d pi l is equal to minus fx delta y delta z. You should know that fx is the normal component, minus fx is the normal component of f along the left side. If you want to calculate the flux, the normal component should be multiplied by area. Therefore, the outward flux of f over the left side is d pi l is equal to minus fx into delta y delta z. Normal component into area. The same manner, the outward flux of f over the right side face is, this is the normal component along the right face into area, delta y delta z. The net outward flux through the two faces is, just we have to add these two, d pi l plus d pi r. If we add these two things, we can get dou fx by dou x into delta v, because d pi l is equal to minus fx delta y delta z, d pi r is equal to fx into delta y delta z plus dou fx by dou x into delta x delta y delta z. These two terms are cancelled, so the remaining term is dou fx by dou x delta y delta z. This is our delta v. So d pi l plus d pi r is equal to dou fx by dou x into delta v. Here delta v is the volume of infinitesimal element. If we calculate the net flux through the other pairs of faces in the same manner, we find the total outward flux for the element volume delta v as d pi total is equal to dou fx by dou x plus dou fy by dou y plus dou fz by dou z into delta v. For one face, for the left face, this is the total flux. For the top face and bottom face, these are all the flux values, dou Fi by dou y into delta V, then dou Fz by dou Z into delta V. Now, for a finite volume V, the total outward flux, here we have taken infinitesimal volume. If you integrate this, we may get for the total volume. For a finite volume V, the total outward flux is integral of this. Integral d pi is pi. Just to take the integral. Triple integral of dou fx by dou x plus dou Fi by dou y plus dou Fz by dou Z into delta V. Here, del dot F is our operator. Del operator value is I into dou by dou x plus j into dou by dou y plus k into dou by dou Z. Dot F vector is I into Fx plus j into Fi plus k into Fz. If you take the dot product, you can get this. I dot I1 dou Fx by dou x. I dot j 0, I dot k 0. J dot j 1 dou Fi by dou Z. Then k dot k 1 dou Fz by dou Z. Therefore, this should be replaced by del dot F, div of F. So, pi total is equal to div of dV. Already we have proved that pi total is equal to double integral of F dot ds. See here, pi equal to F dot ds. Just we have expressed this in terms of area. We have expressed this in terms of volume. Instead of pi total, we should substitute double integral of F dot ds. This is expressed in terms of area. The right hand side is expressed in terms of volume. Now read out this statement. The surface integral of the normal component of the vector function f taken around a closed surface S is equal to the integral of the divergence of the vector f taken over the volume enclosed by the surface S. Gauss divergence theorem relates surface integral and volume integral. Now, divergence stands for emanate or originate. This is a relation between surface integral and volume integral. The above equation shows that the left hand side involves f values on the surface S, whereas the right hand side involves f values throughout the volume V enclosed by S. That's all about the Gauss divergence theorem.